Good evening, friends, and welcome to yet another lecture on chemical engineering thermodynamics. Today we will study about Maxwell's relations. This is a very important topic in chemical engineering thermodynamics. For any differential equation of the type m dx plus n dy is equal to 0, where m and n are both functions of x and y. If we have the relationship dou m by dou y at constant x is equal to dou n by dou x at constant y, then such differential equations are known as exact differential equations. The solution of such differential equation is a potential function of the type fxy is equal to c, where c is a constant. Now, naturally, for such functions, integral from point A to point B is going to be f of b minus f of a. Now, we all know that for a closed system, the first law of thermodynamics is du is equal to dq minus pdv. For a very small change or for an infinitesimal change, we can write du is equal to tds minus p dv. Also, if we add minus dpv on both sides of the equation, the first law equation, we get dh is equal to tds plus vdp. And if we add minus dts on both sides of the first equation, that is du is equal to tds minus pdv, we will get df is equal to minus sdt minus pdv, where f is the Helmholtz free energy. Similarly, if we add minus dts on both sides of this equation, that is dh is equal to tds plus vdp, we will get the differential equation dg is equal to minus sdt plus vdp. Collecting all these equations and putting them down, we get these four equations. Now, the LHS of all these equations are potential functions. It is a known fact that the LHS of all these four equations are nothing but state variables. If we integrate any of these state variables, the value is going to be the value of this variable at the final point minus the value of the variable at the initial point. Now, for a cyclic process, all of these state variables are 0. Therefore, now we get these four equations in the form as shown earlier, that is m dx plus n dy is equal to 0. And since the LHS are nothing but potential functions, all those equations are exact, and the rule dou m by dou y at x is equal to dou n by dou x at y applies to all these four equations. That is, these four equations. So we apply this rule now. We apply the rule of exactness on this first equation, and what do we find? We find that dou t by dou v at constant entropy S is equal to minus dou p by dou s at constant volume V. Similarly, dou t by dou p at constant entropy S will be equal to dou v by dou s at constant pressure P. We can apply the same rule of exactness in the other two equations too, and we get the final results as this. Now, these are the Maxwell's relationships. They have a lot of applications in chemical engineering thermodynamics in solving the various differential equations that we get. We shall look at their applications as and when the situation arises. As of now, this much learning is enough and adequate to understand what is the Maxwell's relationship. That is the end of this lecture. If you have any questions, do write on the comments. If you have a specific demand for a lecture in some area of chemical engineering thermodynamics, do write in the comments. I would be only glad to make such lectures for you. This channel is totally free. The knowledge on this channel is totally free. Therefore, take advantage by going through all my lectures and understanding thermodynamics. If you do not understand anything, let me know. Write comments and subscribe to my channel. Have a great day. Bye.